الله الرحمن الرحيم. In the name of Allah, peace and prayers upon His Messenger, Muhammad, peace be upon him. My name is Iyad Muhammad Awliya. I am a senior student here at the Department of Electrical and Computer Engineering, specialized in information and communication. Last summer, I performed my summer training in the Council for Scientific and Industrial Research, CSIR, in Pretoria, South Africa. As a part of the partnership CSIR has with CACS, King Abdulaziz City of Science and Technology. Including this training, we worked on radar systems, and today I will be presenting a seminar about the introduction of radar and the demonstration of audio radar. First of all, the presentation outline will be introduction, and then radar uses, radar versus other sensors, radar block diagrams, types of radar, pulse radar, range and range ambiguity, range resolution and pulse compression, Doppler processing, and the concept of radar. Radar stands for radio detection and ranging. The practical frequency range of radar systems is from 100 MHz to 100 GHz, but most radar systems operate in the frequency band between 1 and 12 GHz, which is L, S, and X bands in the IEEE standards. Radar systems can determine many parameters of the targets, which is range, angular position, size, velocity, and target identity. This is the IEEE frequency bands standards. You can see that radar systems operates usually in the L, S, and X bands, which is from 1 to 12 GHz. In fact, most of the radars is in these two bands. This is a picture of mid-orbit radar, which is the radar I've worked with in CSIR. As you can see, this is the transmitting and receiving antenna. And in this room, there is many processors, computers, monitors for about 5 persons to work on, which is the whole system of the whole composition of the radar system. Radar uses. There are many civilian radar uses. Maybe most of us will think of radar use just for military use, but in fact there are many civilian uses for radar. First of all, speed traps, and of course the ball speed in sports. You all know in tennis, after serving, they just calculate the speed. Most of them they use ball speed. They use radar to determine the speed of the balls. Collision avoidance in ships and aircraft, natural resources, oil and gas exploration. In fact, CACS now are building a radar to reduce the costs of the exploration of oil in the kingdom. Geology, ice covers, ground compositions, in weather, border control, in aviation, ground control approach. When it's bad weather landing, they use radar to land the aircraft, and also in satellite tracking and spacecraft docking. The military radar use are missile defense, radar guide missiles, ground mapping and surveillance, locating landmines and target tracking. This table here shows the difference between radar and the other sensors. In the operation, radar are first of all, the other sensors that we're going to discuss are thermal sensors, optical sensors, and LiDAR, which is laser radar. In the operation, the LiDAR and the radar are active, and the others are passive. They don't transmit energy while detecting targets. But in the case of radar and LiDAR, we use energy and transmit energy and then receive it to know the targets. When we talk about the range, the most important characteristic of radars, some radar they exceed 400 kilometers in range, while the optical cameras they only take pictures from 25-30 kilometers maximum. And thermal, if you're going to detect ground, it's about 20 kilometers, and 660 for air, and for radar it's just 10 kilometers. And the weather effect. if you are going to take a picture with the camera, of course it will be degraded by the weather if it's raining or fog, but in a radar system it will not affect anything. The angular resolution concept is the smallest angle that the radar smallest angle for radar to differentiate between two targets. If the two targets are in degrees or in milliradians apart, the radar can determine them separately. In the case of thermal, optical, and radar, so it's in microradian. The laser resolution is the smallest range that the radar can detect two targets to be, again, the range resolution is the ability of target to resolve multiple targets if they are very close in range. In radar, this changes from kilometers to centimeters. Sometimes when you are going to detect airplanes, you don't need to have range resolution for 10 centimeters, for example. It can be 2 meters. Because you won't have two airplanes flying with distance from each other about 5 or 6 meters, usually. In thermal, of course, optical, if they are even if they are glass to each other, you will see them. And there is from 10 to 20 meters. The collapse dimension in radar is angles, and thermal or optics range, and radar is also range. The size of the system, of course, you've seen the picture before. How the radar system is big. It's about a room from here to the end of the room. But for thermal, optical cameras and radar, it's smaller than that. This is the general block diagram of radar. You can see that we have a waveform generator for the beginning, and then the transmitter, which goes to the antenna and transmits the energy, got the reflection back from the target, and then that goes to the receiver and to digital converter. Then we have the processing for the radar, which is pulse compression, Doppler processing, detection, and tracking. We'll further illustrate the pulse compression and Doppler processing in future because it's very important here. And then, of course, the display and recording for future use. Types of radar. You can separate radar into main categories depending on the transmission techniques. If you're going to use pulses or you're going to transmit continuously, because this is a pulse and this is continuous wave. Pulse radar are the most commonly used in military application because they have many advantages that we'll consider future, and we'll just go in detail with the pulse radar, not with continuous wave radar. The main parameters in the pulse radar are the pulse width, tau, the pulse repetition frequency, PRF, and the pulse repetition interval, PRI, which is 1 over PRF. As you can see in this pulse, this is the pulse width, tau, the pulse repetition interval of the pulse period time from the beginning of the first period to the beginning of the other period. It's here, PRI, and the pulse repetition frequency 1 over the PRI. And the frequency domain of care, of course, if you take the Fourier transform of this pulse, you will see that it's a sampling function, sin S over x, with this parameters, bandwidth and power, as we said before. Range and range ambiguity. First one, ambiguity means uncertainty or confusion. Target range, the radar can determine the range of targets by simple equation: speed of the electromagnetic waves times the time divided by 2, because this time is the time of the transmitting and receiving. In fact, radar cannot send and receive energy at the same time. This limitation can be solved by this solution, which is transmitting short pulses and listen to the echo of the pulse, and then transmit the other pulse. So we transmit this pulse, and then we'll wait and listen what this pulse return, and then transmit the other pulse until the end. But the problem is transmitting in pulses can result in range ambiguity or uncertainty. How does this happen? If we have this radar and these two targets in front of it, And now we're going to send the first pulse, the blue pulse. When this pulse reaches the first target, the small amount of energy returned from this pulse is this, and this is the continuous pulse will exceed the target and go for further applications. After that, when we're going to transmit the other pulse, the green one, this one will be received at the radar, and we'll see that there is a target at this range. But while transmitting this pulse, and the first one is completely going in the airspace and will have another return from the other target. So we have this return for the first one, and this is coming back to the radar. While the other one, the green one, is transmitting, it will also get a return from the first one again. So at the end, you'll have this one returning to here and this returning to here. The green one will return before the second target from the first pulse returns. So we will have this one here as this target, and then when the green one comes to the receiver, we see that as if there is a target here from the first target. Well, we expect that there isn't any target there. And then when the other one comes, we'll see the other target. So in fact, we'll see three targets instead of two. This is what we call range ambiguity or uncertainty. Now, of course, in this illustration, it was easier because we know that this is the first pulse, this is the second pulse because of the color. But this is how it looks like in a real radar. So you won't know if that's the real target or just an ambiguous image of the first target. So how we solve this problem? Usually, while designing radars, they don't consider the maximum range that the radar can transmit. They have this range, which is a maximum unambiguous range, which is CPRI over 2. So they have a compromise between the PRI and the transmitting of the energy. Range resolution. Range resolution, as we said before, it's the minimum distance in range that two targets can be separated and still be treated as two separate targets by the radar. As you can see here, the two cliffs here are two different targets. But if the two targets are very close in range, they'll appear in the radar as well as one target. The expression here also determines this. If this is a pulse with a pulse width of tau, and these two targets separated in distance, it's just half the pulse width. When this pulse reaches the first target, the amount of energy returns from the first target, and then the pulse will continue and hit the other target. So this yellow amount of energy will be reflected from the other target. Because the targets are very close in range, the two amount of energy comes from the two targets will be came to the radar as a one continuous block, as you can see here. So you will see the target as a one big target, not two different targets. So to solve this problem, we have the range resolution is equal to C tau by 2, which is this distance. So we just need to know that the target is should be distance in more than this distance to be able to detect as two different targets. Usually, if you are going to deal with aircraft and these things, it's in meters, 2-3 meters. But maybe when you're going to deal with smaller items, they would go to half meters sometimes. There is a way which is called pulse compression to resolve this problem. Pulse compression, there is a question why we don't simply reduce the pulse width so we'll have a better resolution. And reducing the pulse width will have many problems because the reduction in pulse width reduces the RF energy. Because if you're going to reduce this to maybe half of it, you'll have the energy. So you won't have that much echo coming from the receiver while receiving. Also, the physical limitation of producing extremely high power pulses with narrow width. So we'll have a technique called pulse compression, which allows us to longer the pulse width and still and to be transmitted, and through processing on the receiver, we'll have a shortened pulse to compromise with the radio resolution. As you can see here, this pulse and this pulse are equal in energy pulses, but this one has a higher amplitude with narrow pulse width, and this one has a larger pulse width with maybe 1/10 or 1/30 of this amplitude. So if we're going to transmit this one instead of this one, we'll have the same energy. There is a pulse compression demo that I will show you now in MATLAB how this works. This is the transmitted signal. If we have for pulse compression, you can see that the time goes from here to here. But when you pulse compress this signal, you have the double amplitude with only this time. Doppler processing. Doppler processing is a technique to determine the target velocities. Also, the Doppler processing can be determined by continuous change in phase of the received signal, which ends up at a change in frequency. This is how the radar detects the velocity of the target. We'll have a video illustration of this coming further. The concept of clutter. Clutter is produced by echoes from unwanted, usually stationary or low frequency or low velocity targets. Trees, buildings, sea waves, all these things will reflect energy and will be there in the radar map. Even rain sometimes can be seen in radar. So this clutter might hide targets since the return is much larger than the target's echoes. Now we'll see a video illustration of the clutter and the Doppler processing.
In this illustration, we see a radar tower with two adjacent mountains. When the radar tower emits a pulse, the mountains cause part of the pulse to reflect back to the tower. When the tower picks up these reflections, they register on the screen on the right. Now we see how a radar tower tracks a moving object. We see how every time the radar pulse hits the jet, a portion is reflected back. The radar display on the right shows the path of the jet. If we fast forward the animation, we can see how a jet being tracked in real time would appear. This is what a radar screen looks like with lots of reflections. See how difficult it is to track the moving object through all that clutter? To solve this problem, we use the Doppler effect, which is the change in frequency of the radar wave when it encounters a moving object. When the pulse hits the stationary tank, it reflects back at the same frequency. However, when the pulse hits the jet as it is moving away, it reflects back with a lower frequency. Finally, as the jet returns, the pulse is reflected back with a higher frequency because the jet is moving towards the tower. All we need to do is add a filter to the radar receiver that eliminates returning pulses with an unchanged frequency. When a pulse returns with a changed frequency, it is allowed through the filter and onto the display. So now when we are tracking the jet on the radar, we only get the moving object with none of the clutter.
They play the video again, it's clear.
It's very clear.
Any questions in the first part of the presentation? Now we go to the second part, which is the demonstration of the audio data I've designed while training there. Audio data is a type of radar that uses sound waves instead of the electromagnetic waves, induction and of the targets. The specification of the audio radar we built in CSIR is the maximum range was 5 meters because we're only dealing with sound waves, and sound waves have problems in attenuation, especially more than the electromagnetic waves, of course. So you can't use the audio radar in outdoor measurements. Just use it inside the room or something. So the maximum was 5 meters. The minimum range is 50 centimeters. The range resolution is 10 centimeters. So if the targets are 12 centimeters apart, they will be seen as 2 targets. If they are 8 centimeters, they will be seen as one target. Sampling frequency is 44.1 kilohertz. This is the general block diagram of the audio radar. First of all, we have the transmitter here. The generation of the sound of the transmitted signal, and then it goes in the complex down mixing process. And on the receiver side, when we pick this target by the microphone, which is our receiver here, we'll bandpass filter it, and then also we complex down mix this, and we pass compress it. Of course, you've seen the advantages of pass compression before, and then cut up into matrix to be mixed ready into Doppler filtering or processing to eliminate clutters and be able to treat smooth targets, and then the display. The transmitter. In the audio radar, we use chirp signal. Chirp signal is a sinusoidal signal that changes in frequency with time. Also, I have a picture. I will show you the chirp signal. Chirp signal in time domain. You can see it's a little sinusoidal, but the frequency changes from a lower frequency to a high frequency with this time. This is the block diagram of the transmitter, as we saw before. The transmitter has generation and then complex down mixing. So the chirp generation, and then the complex down mixing, which is a process of sine and cosine multiplier, and then low pass filter, and the summation of the two branches. If we're going to now we'll go and see how it works on MATLAB. The sound we've heard is the transmitted signal going out from the speaker, reflected by target, and then received by the microphone. This is the transmitted signal time domain, as you see for the chair. And this is the Fourier transform of the signal, which is the transmitted signal in frequency domain. You can see it has two big pulses at the frequency that we've used for transmission. And this is the transmitted chirp tenor pulses, because we're not only transmitting one pulse, there's many pulses as we see, and so on. We saw before pulse the radar. So every pulse of this is a chirp, you can see. Pulse of the chirp. Complex sound mixing is used for many advantages, like conserving bandwidth of sending samples twice as much as you would have taken if you only used in-phase components. This happens because you're using the real and the imaginary part of the signal. If we go again to MATLAB and see how this works. This is here the in-phase component of the transmitted signal, the frequency domain. And when you use the down mixing, which is the sine and cosine branch you've seen in the block diagram, you'll have the other one, which is quadrature down mix component. And then you take the complex number of this signal, so you'll have the complex down mix signal. Now go to determine the receiver of the audio data. The general block diagram of the receiver also, but first of all, when we receive the signal, we bandpass filter it to reduce the noise, the channel amplification that's added to the signal. And then we also process it into complex down mixing again. And then we have the pulse compression and the Doppler processing. So we'll see now how this happens in MATLAB. Finding the figures of the transmitter, so we will not have main figures again. You see the receive signal in time domain. Of course, it's a sound wave, and you can't see it clearly in time domain, so you just take the Fourier transform of it. You can see it clearly in frequency domain. And when you filter this signal, you'll filter the noise here, and then you'll have these two peaks. Now we're just transmitting the wave without putting an object. In fact, now it's maybe reflected from the wall there or something. Yeah. All these signals we see is real mediums from now. We'll have this. Yes, yes. Further, we'll have targets, and then we can see yeah, sorry, I didn't say that. We have all this we've seen now with the real-time distillation because we're using the speaker and the microphone. This is the in-phase component of the transmitted to receive signal also, and then because we are applying the the complex down mixing, and then this is the complex down mixed signal. Now go to the pulse compression. Pulse compressed signal in frequency domain, you can see that the amplitude is doubled many times, and the time is reduced. Now we see the whole picture of the system. This is the last thing that we got from the audio radar, which is the range Doppler map. Here you can see the range of the targets, and here the velocity of the moving target. This might be the wall there because it's about maybe it's not 4 meters, but this is because of the amplification in the channel. When we have now close to targets, we will have this. We'll see this. Now we need one or two volunteers if anybody wants to join. Steve made this up. Now we're going to take this book by this radar here. This book here, here, you can see here. Of course, here you can see that if the target is, if the energy effect from target is high, then it should be coming red. So this here should be the book that was shared before. Another measurement maybe. Okay, this is bigger. So it was the book was about 1 meter apart of the microphone, and it was stationary. So you can see the red dot in zero velocity because it wasn't moving. And of course we can use this target to detect multiple targets, but the problem with sound waves that is distorted with the channel. But here we can try to detect multiple targets. Most of the energy was effected from the first target here, and some of the energy was released from the other target. But now we're going to discuss. Do you need volunteer? No, thank you. Stop it. And now we're going to go for moving targets. Okay, another minute. Okay. You can see here, this here, the power effect from this target, which was almost 70 centimeters from the radar, and the velocity of this target was 0.1 meter per second. And it's in the plus velocity because it was coming towards the target. If we're going to apart from the target, we'll have it here. can see that so it was also about 60 centimeters apart, and this is velocity in minus because it was going out the diagram. At the end of this presentation, I'd like to thank everybody who was who made this training possible, Dr. Ahmed Baramish, and all the doctors from CACS, Dr. Sami Hamedi and Dr. Abed, Dr. Sultan and Devi, and all the people who helped me while training in CSIR, my teammate Faisal, and my brothers, CACS engineers, Engineer Ahmed Balakhtar, Engineer Mohammed Ahmedi, and all the others I have mentioned, and the people who I worked with in CSIR, especially my two supervisors, Engineer Kevin Clocky and Engineer Jack Sealer, and now my mentor, Dr. Yunus Abdul Ghaffar. Thank you very much for your time. Maybe we can see you another time in another seminar.
I think there is time for questions.
Okay.
We saw that transmitter.
First of all, I am really delighted because for the first time I see somebody volunteering to do this seminar for the work that he has done. So how I can thank this guy, I don't know. So it made me so happy today. When he told me yesterday, of course, I was just wondering, but it's a great presentation. Everything is improved, certainly. I have a few points that I wanted to clarify. Once you told me that you are transmitting a frequency of 41 point something kilohertz. Okay? And I thought that you are using some piezoelectric crystals that are used for audio transmission, not high audio transmission, because it is beyond audio range. But later I realized that you are using a microphone and speakers. Is that right?
Yes.
So did you check the frequency response of your gadgets, the microphones and speakers? Are they suitable for the range that you have been using?
In fact, we wanted to definitely at 44.2 kilohertz. So this the frequency is sampling rate for this for the sound card, but we were using 10 kilohertz for transmitting.
I see.
Which is inside the listening band.
When you said 44 point something, I understood because there are already available piezoelectric crystals that will be transmitted at that frequency. Because those crystals, they are going to have narrow bandwidth. So I was just wondering how you fit your chip signals. And because you are not using those, you are using regular. Yeah, I see. Okay, thank you.
How to identify the targets? Is that enemies or some ground?
Of course, audio radar is just for demonstration of, and of course you've seen all the processes that are used in the general free targets are done here. This is just for illustration. When you're going to use electromagnetic waves with targets, you'll have a better image of the target, not just this one, so you can clarify what target is that one, airplane or a car or something. But you won't be able to know if this is your enemy or this is your friend, except if you know that your planes are flying in this direction, so this is coming from another one.
I think for this range, the range is about 5 meters. So the best thing is, if it is in the garden, you may have a dog are better identify the enemy and you know, so because how you identify enemy friend? maybe you have to detect something biomedically to find out the psychology of the guy, not that you can affect. Any other questions, Shabbat? If you start asking questions, you will yes, no.
You saw that the transmitter and the receiver are in the same place. Is it must to be in the same place?
No. Usually they have it in separate places, especially in war cases, because if anything happens to the transmitter, the receiver will be working. But in that CSIR, it was in the same place. Any questions?
But still, you know, if they are in the same place, you have to care for the angle of reflection. You know?
Of course, yeah.
Because it is just a beam going and beam coming, so if it is in the same place, it means you are having direct reflection. Sometimes you have to care for the angle of reflection and spreading of the energy. So if they are not in the same place, you have to care for the spreading of the energy. I'm sorry for interference.
That's okay.
One second. Any modeling? No model, okay. Okay, thank you very much. Sorry. Yeah, but okay, yes.
sometimes radar also becomes a target, especially if we have a audio radar like this. Here it will destroy easily. So we have
No, they have to move it to high frequency anyway, because of the limitation of the sound card here that they are using. They are intentional. Otherwise, they have to. For me, no problem, because I cannot hear anything over 6 kilohertz now. 14 young guys who can hear up to 14 kilohertz. It will be, of course, boring. They are also about 20 kilohertz, 22 kilohertz. It's the frequency for the mice. So if you want to deter the mice, you can use it. But normally they use something like about 40 kilohertz or so. And as you increase the transmission frequency, of course, there are advantages and disadvantages. But in that case, of course, he cannot use the ordinary sound card. He has to design something else.
Okay.
I'm sorry, I just like to have explanation, that's all. No, it's fine. You have a question? Okay, thanks again, Shabbat. I am inshallah expecting to hear similar presentation from all you people. Okay?
Inshallah.
And inshallah, this gentleman will be presenting similar one immediately after 2 months, around 20 December, okay? For his first term presentation. So in that case, I'm expecting, of course, this is a good presentation, but I'm expecting better one. Okay, thank you very much.
Thank you.